This tutorial will show you how to use the hinge joint. A hinge joint constrains the movement of the two connected parts so they can only rotate around one axis. You can set the position of the joint and the orientation for the rotation axis. You can also set the minimum and maximum limits that define how far the rotation is allowed to proceed. There are also controls that determine how the limits react when they're reached. In other words, are the limits springy or are they damped? We'll begin by producing a basic system that's found in all physics textbooks, the pendulum. Create a new project. A copy of this project can be found at C, Program Files, AnimatLab, Tutorials, Body Parts. Please choose where you want to create this project and then name it Hinge. To make some of our calculations easier, we'll be using masses in the range of kilograms. So we need to change the mass and distance units that we're using. Select the environment node and change the distance units to meters and the mass units to kilograms. Now let's add a new organism. Name it Pendulum. Then open its body editor window. Add a root box object. This will be the base that our pendulum swings from. Change its density to be 1 kilogram per cubic meter. Set its height to 0.1 meters and make sure that we freeze it in place. This pins the part in space so it can't move. Now select Sphere as the default body part type and leave Hinge as the default joint type. Add a new sphere to the root. Set its color to be blue. Then change its density to 1 kilogram per cubic meter. And then name it Pendulum. Set the X rotation to 0. Then change its radius to 0.2 meters. Set the location to be 0, -5, and 0 meters. Now we need to zoom out so we can see the pendulum. Select the joint and name it Hinge. Set its location to be 0, 5, and 0 meters. This will make the length of our pendulum 5 meters. If you zoom into the hinge, you can see that it has two flaps and an arc that defines its range of movement. Right now the movement's not quite what we want, so rotate it around the z-axis by 90 degrees. Now the pendulum rotates back and forth just like we need it to. Before we run the simulation, let's push the camera out a bit further so we can see everything. Set the offset to 15 meters. Now run the simulation. We can use the mouse to grab onto the ball of the pendulum and apply force to make it begin swinging. Notice that the ball only rotates in one direction. It doesn't translate or rotate along any other axis. Now let's add a motor velocity impulse to start the pendulum swinging automatically. This will cause a motor to come on for just a moment to raise the ball up and let it go. Change its name to be Impulse and set its end time to 1 second and velocity to 1 radian per second. The ball didn't swing. This illustrates an important point regarding the motor velocity stimulus. When it ends, the motor will still be enabled and will try to maintain a zero velocity. So when this stimulus ended, it was locking the pendulum in place and not allowing it to swing. We can change this though by setting the Disable When Done flag to be true. This will disable the motor and allow the joint to move freely. This time our pendulum swings like it should. Now let's do a simple test to verify that the period of our pendulum is correct. Change the motor stimulus to only apply a very brief impulse so that the angle of oscillation remains small. Change the end time to 0.1 seconds and the velocity to 0.1 radians per second. Now add a new line chart and add items to view the rotation angle and velocity of the hinge joint. Run the simulation. Now view the data from the chart and look for places where the velocity becomes zero. We want to find the time it takes to complete one full cycle. The first point occurred at time 3.369 seconds. The second point occurred at 7.857 seconds. This gives us a period of 4.488 seconds. The standard formula for calculating the frequency of a simple pendulum is the square root of the gravity divided by the length. In this case, the length is 5 meters, so we get a frequency of 1.4 hertz. We can use this to find the period by dividing 2 times pi by the frequency. This gives us 4.488 seconds, which matches what we got from the simulation. We should note here that this equation is only valid when you assume small angles. That's why we decrease the motor velocity stimulus. According to these equations, the period of the pendulum is only dependent on gravity and its length. So let's decrease the density of the sphere to 0.5 kilograms per cubic meter and see what, if any, effect this has on the period of the simulation. The velocity is zero at exactly the same points. So, as the equation predicts, changing the mass of our object made no difference on the period of its swing. Now let's try and shorten the length of the pendulum. Change its length to be 3 meters instead of 5. This time the velocity reached zero at 2.611 seconds. And then again at 6.09 seconds. This is a period of 3.479 seconds. When we use the equations, we get a period of 3.475 seconds. As I mentioned before, the equations we're using are only an approximation, but our two numbers are still very close. Now, let's look at how the limits on the joint work. Let's rotate the base of the pendulum over so that the arm is sticking out so that gravity can push it down. Select the root object and rotate it around the z-axis by 90 degrees. Select the hinge joint. The hinge has two flaps on it that define the limits for motion around that joint. You can change the limits by using the mouse to click on the circular selection points and then dragging to move them. You can also directly use the max and min limits properties to set them to a specific value. Let's set the max limit to 45 and the min limit to negative 45 degrees. Now the pendulum won't be able to rotate further than that angle. Disable the motor stimulus. Then let's move the camera in a little closer. Set the offset to 8 meters. Run the simulation. Now gravity pushes the pendulum down till it reaches the limit. The limit is slightly springy, so it bounces off and then settles down eventually. Let's see how to control the springiness of the limits. Constraint limits act like springs that have both a stiffness and a damping. If we increase the damping, it will cause the object to come to rest faster by bleeding energy more quickly from it. Set the damping to 100 grams per second. Now it only has one small bounce. The coefficient of restitution is the ratio of the rebound velocity to the impact velocity when the joint reaches the low or high limit. Increase this value to 0.3 and let's see what happens. This time the restitution force is much larger and we get a very springy limit with numerous bounces till it finally settles down. When we set the parameter back to 0, we again only have the single bounce that we saw before. Now decrease the stiffness of the limit. Set it to be 1000 newtons per meter. Since we've decreased the stiffness, the damping is now large enough to overcome the restoring force and prevent any bounces when the sphere hits the limit. You can use these properties to control the limits of rotation and the types of limits that you want in your organism.